Hello students, welcome to the lecture 14 of this course, which is named chemistry. The course code for this particular course is CH101 for the odd semester and CH201 for the even semester. This is G. Chakraborty and you are watching the lecture number 14 of this subject, which is called chemistry. Now, as you can see, lecture number 14 is nothing but the last and final lecture of use of free energy in chemical equilibria. Now, in the last 5 lectures of this particular part, we have seen different aspects, like we people have come across the parts of thermodynamics, that is how many different properties of thermodynamics are there, and what is thermodynamic system, what is surrounding and all. Okay, these total things we people have seen. Now here in this particular lecture, one thing is that here we will be dealing with multiple things, because this is the final lecture of use of free energy in chemical equilibria. In the last 5 lectures we have come across thermodynamics. Here we will see electrochemistry. Okay, so let us move into this lecture. So welcome again to the use of free energy in chemical equilibria, the part 6. And as we move into the lecture, we can see, yes, the topic of electrochemistry has come up. Electrochemical cells, electrolytic cells, how to write down a cell, standard electrode potential and its calculation, electrode potential, EMF, and Nernst equation. Okay, so let's see gradually what we people can do. Now, as you know, electrochemical cells and electrolytic cells are the 2 types of cells available. Now, what is a cell? The preliminary question arises, what is a cell? Then we will say cell is combination of batteries, right? A cell is nothing but combination of batteries. Now, what these batteries mean? These are the batteries which actually gives power to some certain compound, right? So jokes apart, cells are, yes, they're combination of batteries, and cells are of 2 types. One is electrochemical, another is electrolytic. Now, electrochemical cells are of multiple types again. It can be voltaic cell, can be galvanic cell, can be Leclanche cell, can be Daniel cell. Right? What is the difference between these 4 cells? Anybody can tell me what is the difference? The main difference is that the names are different. Is that so? Answer is partially correct or wrong? The answer is partially correct. Okay, names are different, arrangements are different, that's why the cells are different, but all of them are of the same category, that is electrochemical cells. Okay, now let us see what is written. An electrochemical cell is a device capable of either generating electric current from chemical reactions or generating electrical energy to cause chemical reactions. Okay, the electrochemical cell which generates and electric current are called voltaic cells or galvanic cells. So basically these are the cells which will convert chemical energy to electrical energy, and the most common examples that this particular type of reactions like is the voltaic cell and galvanic cell, because they generate electric current from the chemical reactions. Now this was the definition, but what about the working? Let us see. We are having let us clear the lines out. Okay, now in this particular structure we are having 2 electrodes. One is the zinc electrode, another is the copper electrode. So definitely the zinc will be anode and the copper will be cathode, and it is written in the picture also, right? Now what will happen, as zinc is anode, so it is minus, copper is cathode, so it is plus. Now electrons will move from anode to cathode, right? Current will move from cathode to anode. Okay, so this type of thing occurs. You can see one porous disc is given. It is not a porous disc, basically it is a salt bridge. right? And these two different electrolytes are separated by the salt bridge. If you just connect a light across, you will get a bulb across, you will get some light. Okay, so this will prove that your particular cell is working. Okay, so this was electrochemicals. Now here comes electrolytic cells. So what are electrolytic cells? Electrolytic cell is basically the anti-member, the opposite member to that of the electrochemical cell is electrolytic cell, because this particular cell uses electrical energy to drive a chemical reaction. Okay, so one chemical reaction is not happening, just you are supplying some electricity, the reaction started. Okay, and an electrochemical cell is a kind of sorry, an electrolytic cell is a kind of electrochemical cell, special kind rather. It's very often used to decompose chemical compound, process called electrolysis. Yes, electrolysis is the process that we have used multiple times in the lab, and this particular process is used uh, for the separation of one species from the other. Okay, the Greek word lysis means breakup. So breakup means separation, nothing else. Important examples of electrolysis are the decomposition of water from hydrogen and oxygen, bauxite into aluminum, and other chemicals. Right. The first one is very important. Hydrogen and oxygen are splitted from water. Okay. Now electroplating is done using an electrolytic cell. Electrolysis is a technique that uses direct current. Okay, so DC current it will use, AC current it will not take, and electroplating can be done using this particular process. Okay, so let us have a look at the cell that we people are having. As you can see, there are two electrodes. One is anode, another is cathode. Simply aqueous NaCl is given, and it is getting electrolyzed. Okay, so this is what electrolysis is. Okay, it's another beautiful diagram that we people can see here. This beautiful diagram seems that electrolytic and electrochemical cell has a wide difference between them, and the pictures are also present here. Okay, so let us go for electrochemical cell first. So it is at the right side. Let us go for electrochemical cell. So first point is saying electrical energy is produced at the expense of chemical energy. Basically, electrical energy is produced from chemical energy, and electrical energy results in a chemical reaction. Very important point. Here, in the electrochemical cell, chemical energy is resulting in electricity formation. In electrolytic cell, electricity is resulting in chemical reaction formation. Okay, right? Anode is negative, anode is positive. Okay, cathode is positive, cathode is negative. Fine. People will die by confusion. Okay. Electron move from cathode to anode through external circuit. Electron move from anode to cathode through external circuit. Yes, if you have reversed the electrode, this will happen, right? EMF of the cell depends on the concentration of electrolyte and nature of electrode. The extent of chemical reaction depends on Faraday's laws. Okay, so electrochemical cell will depend on the electrode, the nature, the material, the electrolyte, but electrolysis will depend only on Faraday's law. EMF is produced by potentiometer. Electricity is measured by coulometer. So two different types of apparatus is given here. One is coulometer, another is potentiometer. And last but not least, the seventh point is saying two different electrolytes and two different electrodes are used. One electrolyte and two electrodes of the same element are generally used. Okay. So see, electrolysis is much more different than that of this particular example. Right now, this is the electrolytic cell. There is a galvanic cell. You can see in this particular cell. If we connect the anode and cathode, then the bulb will be lighted. And here, what is happening? You are just giving electric supply, and this electric supply is resulting in chemical reaction inside the electrolyte. Okay, right? Understood? This is the main phenomenon. How electrolytic cells work? Basically, they pass electricity through some solution, and the solution gets separated. Okay, that is electrolysis, and it is also called electroplating if it is precious. Let's see. Okay, now this is also very important. I love this page. Why I love this page? It's quite beautiful. And voltaic cell notation, here you will see how to write down a cell. So voltaic cell can be described using shorthand. Fine. Let us consider this particular reaction. It's the most common reaction in the world, that is Zn plus Cu2 plus gives Cu plus Zn2 plus. Okay. Now we need to write down the half cells. Now what is a half cell? Zn. Let us write it down properly in a proper manner. Zn. This will result in formation of Zn2 plus 2 electron, and Cu2 plus, it keeps Cu2 plus 2 electron will give Cu. Now the condition is we need to write down which one is which one, which is oxidation of, which is reduction of. See, zinc was previously in Zn form, it is becoming Zn2 plus, so this is nothing but oxidation half. Obviously the second one will be reduction half. Okay, now what we need to do, we need to just display the oxidation and reduction half in such a way that oxidation will be at the left side of the salt bridge, and reduction will be at the right side of the salt bridge. Why this is like that? Just simply follow alphabetical order. A comes first, so anode is coming first. Okay, or oxidation comes first, then reduction comes second. Okay, that's it. Let us go to the next slide. Standard electrode potential and its calculation. So what is standard electrode potential? It is defined as the individual potential of reverse electrode standard state when ions having concentration of this and 180. Okay, therefore standard electrode potential is commonly written as standard reduction potential. Fine. Okay, so as you can see, zinc copper system is 1.10 volt, zinc CO system is 0.51 volt. So this implies that potential difference between copper and cobalt is 1.10 minus 0.51, that is 0.59 volt. Okay, this is exactly the potential measured by standard conditions of the cell constructed with cell diagrams. Right, so this value we get actually whenever we do test. Okay, now here the cell is written as it is, right? Whatever I have told you people, in a similar manner this particular thing is written. Okay, and beside the E0 value is also written, so it is quite good. Now the cell diagram represents the oxidation of cathode and reduction of copper. Fine, all tabulated values and standard are listed below. They are basically saying that you just take the data and just calculate it out, and we will calculate, definitely we will calculate using this particular formula. E0 cell is equal to E0 cathode minus E0 anode, or by the Nernst equation. We will calculate it. Now this is the Nernst equation and EMF, as you can see. So electromotive force, or EMF, there is energy per unit charge and all, right? It's by an energy source such as an electric generator or battery. Okay, basically let us try to understand what Nernst equation is giving us. This particular equation is called the Nernst equation. This is the Nernst equation. Now here multiple things are present. I just want to sorry, yeah. So multiple things are present. I just want to see that which one will give us the best result. In electrochemistry, the Nernst equation is an equation that relates the reduction potential of electrochemical reaction to the standard electrode potential and activities of the chemical species undergoing reduction and oxidation. The activities are to be monitored using Nernst equation, and also the different documents, just like what is delta G and how the things are calculated. This type of things will be discussed. Okay, so we will not doing for the above steps. We'll do after this. E cell equals to E0 cell minus RT by NFL Q, or E cell equals to E0 cell minus 0.059 by N log Q. This Q is nothing but reaction quotient, or for a normal reaction, AA plus BB gives C plus DD. You know, C and D will be at top. There is a products, and A and B at the bottom. Okay. Now that is Q. Okay. Now if R is 8.314, T is 298, F is 96500, then this type of value will come. So always remember, this type of equation is used to solve the numericals, right? This is quite important for us. Okay. Now this is the numerical that we need to solve, and the numerical is very simple. Mg plus 2Ag plus Mg2 plus 2Ag. Okay, E0 cell value, E cell value is given, E0 cell value is given, E cell is to be found out. The reaction is written here. Now we will try to write down the cell. So how to write down the cell? Let us see. Mg becomes Mg2 plus. That means it is the oxidation arm. Okay. So we will write Mg slash Mg2 plus. Sorry. Double line. Then we are having Ag plus slash Ag. Okay. This is a cell. Now what we are going to do? We are going to write the Nernst equation. Okay. E cell equals to E0 cell minus 0.059 N log Q. Right. Now why I have written this? This is quite simple to understand that why I have written this. This one is right. This one is left. Okay. Now E0 cell is given here, so E0 cell need not be mentioned. So what basically we are going to do? We are going to write E cell is equal to 2.303 by N, not N, let it be 2 log this particular species, this one into this one, divided by this into this. Okay, so at the top here we'll write Mg 2 plus, and we'll write Ag within power square bracket, right? And here we'll write Mg and Ag plus square bracket. So this will go off, right? So finally we'll get Ag divided by Mg. Okay, and for Ag divided by Mg, if we are putting the value of this particular thing, then sorry, I told you the wrong. It will be Mg2 plus divided by Ag plus. Mg2 plus divided by Ag plus. So at the top there will be 0.130 molar. Here this particular value will come up, and here this particular value will come up at the denominator, and we'll be getting our desirable answer, right? Okay, so that's all for the day, and that's all from the use of free energy in chemical equilibrium. So 6 lectures under this module has been finished. 2 more lectures are going to start, right? And that is from a different topic, which is called real gases. So this is all about thermodynamics and electrochemistry. This is Jeet Chakraborty signing off for use of free energy in chemical equilibrium.